Recapping our previous work, there are situations when there may be no diversion available for a large part of the flight. Oceanic transits, such as this one over the Atlantic, are one example. The point of equal time is defined as that point along track from which it will take the same time to fly to one of two airfields. If an emergency were to occur after the PET, it would be quicker to go on. And if before the PET, it is quicker to return. The point of equal time therefore occurs when time on equals time home. It is affected by wind component along track, so will vary from flight to flight, even along the same route. It can be found from the formula that x equals d times h over O plus h. This is the starting point for all point of equal time questions. Up until now, we have assumed that the wind component remains constant all the way along the route. For instance, in this example, we had a total distance of 500 nautical miles and a true airspeed of 300 knots. The wind component was 60 knots head. This was valid for the whole of the route. This made O, the onward ground speed, 240 knots. And H, the homebound ground speed, was 360 knots. We substituted into the equation x equals d times h over O plus h, and calculated x to be 300 nautical miles. This gave us a distance of 300 nautical miles from the departure airfield to the point of equal time. However, this idea of a constant wind component all the way along the route does not always reflect reality. Over a long track, such as the North Atlantic, the wind may well change, particularly if the route crosses a weather front. We're going to show this in the following scenario. We have a route distance of 2,050 nautical miles, from last point of diversion A to next available diversion B. The aircraft's true airspeed is 475 knots. When we start off, the wind component is 45 knots tail. We're going to assume that the wind changes approximately halfway along the route, close to where the point of equal time occurs. Clearly, this is something of an assumption, because the wind itself affects the position of the point of equal time. However, wind forecasting is not always a precise science, and this supposition is going to be near enough for practical purposes. From the point of equal time onwards, the wind component is assumed to be 10 knots head. This means that O, the onwards ground speed, is 465 knots, and H, the homewards ground speed, is 430 knots. Now we substitute into our usual equation x equals d times h over O plus h. D is 2,050, O is 465 knots, and H is 430 knots. If you get your calculator out and do the maths, you will find that the distance to the point of equal time is 985 nautical miles. Just so that you get used to the terminology, we'll use the term critical point for the point of equal time from now on. It's almost as common, and you should be familiar with it. We now need to work out the time to the critical point. This is an important piece of information, as we shall shortly show. The first thing to notice is that the ground speed to the critical point is not O if the wind changes. O assumes a headwind component of 10 knots. But out to the critical point, the wind component is 45 knots tail. Therefore, a TAS of 475 knots, plus a tailwind of 45 knots, gives a ground speed out to the critical point of 520 knots. So our time to the critical point is 985 nautical miles at a ground speed of 520 knots, which comes to 113.5 minutes. Let's check the algebra out now. If the distance to the critical point is 985 nautical miles, and the total distance d is 2050, simple subtraction tells us that d minus x, the distance onwards from the critical point, is 1065 nautical miles. If you get your calculator or nav computer out, you find that the time onwards, that is 1065 nautical miles at 465 knots, comes to 137.5 minutes. And the time home is 985 nautical miles at a ground speed of 430 knots, which also comes out to 137.5 minutes. There are some emergencies that require a landing as soon as possible, but do not involve a change of true airspeed. A sick passenger or perhaps a generator failure might be examples. However, in many instances, an onboard emergency will involve a loss of altitude. For example, an engine failure will result in a drift down to a stabilizing altitude, and a pressurization failure would require an immediate descent to 10,000 feet. This will almost invariably involve a loss of TAS. We are now going to assume that flight at a lower altitude following an emergency has reduced our TAS to 380 knots. This will affect our ground speeds. O, the onwards ground speed, is now 370 knots. And H, the homewards ground speed, is now 335 knots. As always, X equals D times H over O plus H. D is 2050. O is 370 knots. And H is 335 knots. Again, get your calculator out and do the maths. The distance to the critical point is now 974 nautical miles. Now let's see what the new time to the critical point is. There is an important point for you to understand here. Even though we are dealing with a one-engine-out critical point, we still use the all-engine TAS to find the time to it. If an emergency necessitating a reduced TAS were to occur before the critical point, it would be unthinkable to continue onwards to it. You would go back. You don't need to know the one-engine-out time to the critical point. You would never use it. Emergencies do not occur on the vast majority of flights. They proceed without incident. However, when we are flying on a normal, all-engines routine flight, we still want to know whether we have reached the one-engine-out critical point yet, in order to allow us to make a decision where to go if we should lose an engine. We therefore calculate the time to the one-engine-out critical point at the all-engine speed. As before, a TAS of 475 knots, plus a tailwind of 45 knots, gives a ground speed out to the critical point of 520 knots. This time, our time to the critical point is 974 nautical miles, at a ground speed of 520 knots, which comes to 112.5 minutes. Let's compare the answers we got for the all-engines critical point and the one-engine-out critical point. Using the all-engines TAS after the critical point, the distance to the critical point was 985 nautical miles, and the time was 113.5 minutes. Using the one-engine-out TAS after the critical point, the distance to the critical point was 974 nautical miles, and the time was 112.5 minutes. At first sight, this seems like a pretty remarkable result. The TAS from the critical point has reduced from 475 knots to 380. That's very nearly 100 knots. And yet the position of the critical point has moved by only 11 miles over a route distance of 2,000 miles. Why is this? Think about it for a while and try to come up with your own answer before you click to continue. The reason that we get such a small shift in the position of the critical point, even though the TAS has changed by nearly 100 knots, is that the position of the critical point depends on the ratio of O to H. If the wind component is not very strong in comparison to the true airspeeds involved, that ratio does not change much. The ground speeds change significantly, but their ratio to each other does not. In this example, O included 10 knots headwind, and H included 45 knots headwind. That is a difference of only 35 knots headwind. Whether the TAS is 475 knots or 380 does not make a lot of difference to the ratio of the ground speeds. Now, the idea of the critical point is that it is pre-calculated as part of the flight planning process. Then, as the aircraft passes over the last point of diversion before the oceanic leg, the actual time of arrival is noted. The pre-planned time to the critical point is extracted from the flight plan and added to the actual time of arrival over the last waypoint. This takes all the decision-making out of in-flight emergencies. If one should occur, there is no frantic searching through charts or rapid calculation in the air. The decision is a simple one. If the time is less than 112.5 minutes after the last waypoint, we turn back. If it is more, we go on. We do not want to complicate this decision by having different critical points for different situations with different ETAs. Because the difference between the 2 points is usually quite small, we always take the one engine out situation. This covers the worst case, so this is the calculation we use. The all engines time to the critical point is usually very similar whether we take the all engines or the one engine out point. However, if we use the reduced TAS after the critical point, the time to the alternate airfield will obviously increase. The distance to the one engine out critical point X was 974 nautical miles. With a total distance d of 2,050 nautical miles, the distance onwards from the one engine out critical point is 1,076 nautical miles. O, the reduced ground speed onwards, is 370 knots. And H, the reduced ground speed home, is 335 knots. As before, if you get your calculator or nav computer out, you find that the time onwards, that is, 1,076 nautical miles at 370 knots, comes to 174.5 minutes. And the time home is 974 nautical miles at a ground speed of 335 knots, which also comes to 174.5 minutes. The time we calculated using the all engine speeds after the critical point was 137.5 minutes. This is shorter by 37 minutes. Sometimes you are given wind velocity and track instead of component, and you have to calculate O and H yourself. Here is an example. The track between A and B is 030 degrees true, and the distance is 500 nautical miles. The aircraft has a true airspeed of 180 knots. The forecast wind all the way along the route is 35 knots from 090 true. What is the distance and time to the PET? We first need to find O. Plot the wind velocity of 090 at 35 knots on your navigation computer. Rotate the inner scale to put the outbound track of 030 against the 12 o'clock index, and move the speed scale to put 180 knots TAS under the centre circle. You can see that this gives an initial 11 degrees of port drift. You now need to balance the drift in order to get an accurate ground speed. Rotate the scale until the heading reads 040 degrees, with 10 degrees of port drift. This gives you a track of 030. This gives O as 160 knots. Now we find H. If the outbound track is 030, the homebound one must be the reciprocal 210 degrees true. Rotate the inner scale to put the homebound track of 210 against the 12 o'clock index, still keeping 180 knots TAS under the centre circle. You can see that this gives an initial 9 degrees of starboard drift. Balancing the drift again, rotate the scale until the heading reads 200 degrees, with 10 degrees of starboard drift. This gives you a track of 210 and gives H as 195 knots. The TAS was 180 knots. Notice that O was 160, giving a 20 knots headwind component. H is 195, giving you a 15-knot tailwind. This becomes obvious when we look at the triangle of velocities. The outbound track is 030. Plot in the wind, 090 at 35, downwind. With a pair of compasses, draw arcs corresponding to 180 knots of TAS, and draw in the lines corresponding to the air vectors. This is O, with its heading of 040, and this is H, with its heading of 200. You can see that the geometry of the triangle of velocities does not always give a tailwind component of the same value as the headwind reversed. You have to solve the triangles with a navigation computer in both directions. If you make approximations of the wind component, using rule of thumb methods, or assume that the tailwind component is the headwind component reversed, you may well get the wrong answer. Let us summarize what we have covered. Point of equal time, or critical point, can be found from the formula x equals d times h over O plus h. This is the starting point for all point of equal time questions. Some calculations assume a constant wind component all along the route. However, the forecast wind may well vary over the flight. This is not a problem, because the equation deals with this situation as long as the wind change point is assumed to be the critical point. Forecast wind along a route can be split into two halves, and then averaged over each half. Emergency situations may also result in a loss of altitude and power, and consequently a reduction in TAS. The same equation also covers this case, as long as the reduced TAS is used in the calculation. However, if a reduced TAS is used to calculate the position of the critical point, the time to the critical point is still based on the all-engines ground speed. Unless there is a strong wind component, there is usually little difference between the position of the one-engine-out critical point and the all-engines critical point. In order to keep the decisions simple, we use just one point of equal time. This is always the one-engine-out case. And finally, if you are given wind velocity and track instead of component, and you have to calculate O and H yourself, you have to solve the triangles with a navigation computer in both directions.